with PowerPoint. Okay. I'm introducing. Speed it very simply.
Yeah, you have done your own sheet. Just copy all that out. Just get rid of that. Cut this bit out of here.
Alright.
Okay, so William is going to talk about piecewise smooth extremals from the new territory of Frederick Wann's book.
Alright, so the topic of my talk is obviously piecewise smooth extremals. So we're looking to optimize basic functionals or basic functions of f, x, y, and the derivative of y. But the case that we're going to examine is where the function might not have a continuous derivative, and therefore it needs to be treated differently than some of the functions that we saw last week. Now, first thing we need to define is piecewise continuity. So a function is piecewise continuous if it can be seen as continuous over a finite number of subintervals. So you can chop up the domain as much as possible, but there has to be a well-defined value for each value of x in the domain. Just moving quickly, a piecewise smooth function is one that is continuous over the entire interval, but the intervals must match up and have the same values at their boundaries, and then the function must be differentiable, and the derivative must be at least piecewise continuous. Now, we are going to try and use these definitions, or at least use a Lagrangian with this definition of piecewise smooth to try and solve a basic optimal problem of J of y. Now, starting from basics, we're going to go with fixed endpoints because we haven't really gotten that far yet. Before we move on to more complicated problems, we're just going to start with the basics of fixed endpoints. So I think for the first few chapters, we only deal with fixed endpoints. Now, in order to find maximum or minimum for J, we have to look at a set of admissible comparison functions, y plus epsilon h. Now, I tried to keep the notation as superfluous as possible with Kevin and Maggie's talks, but because of some long derivations, I didn't really use an eta instead of an h. But nonetheless, we have our set of epsilon functions where the concept is the same as we saw last week, where we're looking around the vicinity of our extremal y, and we have vanishing points for h and very small epsilon. So we're looking at a set of functions that are like y, but not quite. So when we plug in this set of admissible comparison functions into J, we get a function of epsilon. So when we have the function of epsilon, we can differentiate with respect to one variable, and then once the derivative equals 0, we can find a maximum or a minimum point. Now, there's this one thing that we look at in this chapter, which is that these are only called weak local minimums and weak local maximums because we have this constraint on the admissible comparison functions. So we're only looking at a particular set up and down, so we can't really class it as a strong local minimum or maximum, which is covered in later chapters. So, if we differentiate with respect to epsilon at epsilon equals 0, we get a maximum or a minimum or a saddle point, but we need this condition to justify an optimum value. So this, apologies for my whiteboard writing, but this expression here is the one that we got last week, and we used it to derive the Euler differential equation. The problem is this time we don't have a derivative term. Like, you cannot differentiate twice. You can't use that to in the Euler differential equation. So we have to find another equation to use, one that will allow us to optimize piecewise smooth equation. Now, this time, last time we differentiated with respect to this, and integrated by parts with respect to this, and we received a term which became n of x, h of x, and used the fundamental lemma of calculus of variations to prove that it was 0. In this one, we have a little bit more of a messier case, because we integrate by parts with respect to this one, but there are a few steps that need to go on before we get to here, which is what we want. Now, we start by, I'll just switch over to the projector, fingers crossed. We start by comparing this equation here to a basic form, which is the integral m of x, h of x, plus n of x, h dash of x, where m and n are arbitrary functions of x. Now, we're going to we just need to note that m of x in this case will be equal to partial of df to dy, and n of x is equal to the partial of df dy dash. Now, because we're integrating by parts with respect to this term, we let beta of x equal the integrand of n. So what we do is we now integrate this term by parts, and we get beta of x, h of x, beta a minus b. And this all equals 0 because it's a critical value of the function with respect to epsilon. So because of the m conditions we put on h, this term equals 0, and so we get the form n of x minus b of x times h dash of x dx equals 0. Now this is a tidier form that we can use, but we can't use the fundamental lemma of calculus of variations on the h dash of x term because the function f is not twice differentiable. So what we need to do now is a bit tricky because we need to make some clever choices for a constant that we can insert and some clever choices for the h term. So basically what we want to do is administer this constant c equals basically, sorry, what would be minus a n of x minus beta of x dx. So mirroring this term here, but this constant out the front becomes apparent so that you can satisfy n conditions when you plug it in to the function later. So c times b of a h dash of x equals 0 because because of the boundary conditions on h dash of x, on h of b equals 0. So we can plug this c into the equation that we have here. And so we get n of x minus beta of x minus c times h dash of x dx.
We can't see.
Just push your page up.
Oh, sorry.
Lovely.
Alright, and now because h of x is an arbitrary function to find vanishing points, we can choose any function that is 0 at the boundaries. So if we make the clever choice of the integral of n of x minus b to the x minus c, which is also mirroring this term here, we find that h of a is trivial because it cancels with this term. Sorry, it's from x to a equals 0, and h of b becomes 0 because of this constant c. And so h dash of x equals n of x minus beta of x minus c. And so this whole equation, equation 2, which I define up here, becomes the integral of u of a n of x minus beta minus c squared 0. So now we have equation 3, which is very useful because n of x minus b of x minus c is non-negative. And because it's piecewise continuous, if the integral equals 0, the function inside equals 0. So n of x minus beta of x minus c squared equals 0. And so n of x minus beta of x minus c equals 0. Alright, so we have this result, n of x minus beta of x minus c equals 0. If we sub back in the values, so we can translate it back into functions of f, we get what is the Euler-Lagrange equation, or the first statement thereof. So n of x equals c plus beta of x, n of x, where we define n of x before as df dy dash equals c plus, sorry, this is I'm substituting two terms. So this is a very important equation, the Euler-Lagrange equation, which, going back to the projector, it's kind of very powerful because none of these terms are differentiated twice. So now we have a whole new set of equations that can be solved, a whole new set of Lagrangians that can be solved using this equation without needing them to have two continuous derivatives. One particular corollary of this equation is this term here, which unfortunately I don't have time to go through, but it comes from parametrization. It comes from equating that to the some other term. I'm sorry about that. Using this equality and the Euler-Lagrange equation, because they're equal, we can use them both to solve problems. So now that we have the tools of the trade, we have to define some sort of limiting conditions on what we can solve. So these can be called, well, the most fundamental conditions, limiting conditions in piecewise smooth extremes are corner conditions, which were developed by Erdmann, and Weierstrass. Now, just on a funny side note, I found while I was researching that Weierstrass is participating on a lot of famous theorems in the world, but his name always appears second. So,
oh yeah, it was another Weierstrass.
He doesn't get the recognition he deserves. I think maybe one theorem features his name first.
It's all in alphabetical order.
Pure mathematics, or mathematics generally publishes in alphabetical order.
Okay.
My name is C.
It's not a very happy portrait. But anyway, moving on. So these corner conditions that we use to define what the problems we can find are the partial derivative with respect to y dash must be continuous, and so must this quantity, which is convenient because we have a statement of the Euler-Lagrange equation which we found before, which I explained terribly well, which must also be constant across this interval. Now, we can use this by equating the left and right hand limits. So we equate the left and right hand sides of the function and see if that implies that the left hand limit and the right hand limit of the derivative are equal. So if these two limits of the derivatives are equal, it is not a corner. So if there are no corners in the thing, we can solve the equation. Corners are bad. Perfect. So in order to check for corners, we set P equals the y, the limit from the left, and Q equals the limit from the right, and then we see if the equation implies that they are equal. So now we'll put these equations that we found and the conditions to the test with minimizing surface area problem. So unfortunately, due to the fickle nature of the one textbook, I couldn't find any terribly demonstrative examples of piecewise functions to use, which is quite ironic. But you can use this example to show how we check for corner conditions, and then how we can use the Euler-Lagrange equation, which works for most functions, to derive an important result. So, just for the purposes of making sure we get out of here by midday, I'm going to take out the 2π constant on this, and we're just going to address the extremal where, swapping back to the, we'll address the extremal where f of x of y equals squared. So, checking for corners, we find df dy dash to be y times y dash over root 1 plus y dash squared, and f minus y dash df dy dash to be y squared. So, as mentioned before, we set the left-hand limit of the derivative to be p and the right-hand limit to be q. And so, equating the functions, we go, we'll start with the first one. Plus p squared equals y cubed over 1 plus q squared. So, in this case, if y equals not 0, is not equal to 0, this implies that p equals q. And then we check the second condition, where y on root 1 plus p squared equals y on root 1 plus q squared. Again, we get this condition that if y is not equal to 0, p equals q. So we have to examine y equals 0 case first. Check we can proceed. Yeah?
Oh, sorry, I may be completely wrong, but in the first equation, have you missed a minus sign? Partial of f with respect to dy. Is there a minus there?
No. So, partial with respect to y dash.
Oh yeah, sorry. Yeah, sorry. I was confused.
So we have p equals q for every case except for y equals 0. So if we examine this case, y equals 0, we find that it's trivial and not valid because it doesn't satisfy our end conditions. So we set up for where y of a equals a and y of b equals b. So if a and b are non-zero, this equation is not, this case is not valid. So we can proceed with our optimization. So if we use the corollary from the Euler-Lagrange equation, we can perform our extremal quite easily. So we use this quantity f minus df, y dash df dy dash equals constant if x does not depend explicitly on x. So we will take f minus y dash df dy dash that we found earlier and set it equal to some value c naught. Now, this through a couple of steps becomes a separable equation. So we get equals y minus c naught, and eventually dy dx equals minus c naught squared minus c naught, which becomes standard form, the inverse cosh. Okay, so rearranging this, we get a general form for our minimal surface area curve between two fixed endpoints, which is y equals c naught cosh x on c naught plus c1. Alright, so similar to the catenary problem, we get a cosh curve, and it turns out the minimal surface area, the curve that minimizes surface area is a catenoid, which is rotated about the axis. And so I'm going to jump on this opportunity to go all the way through with an example, because we haven't, in the talk so far, we haven't made an analytical solution. So I'm almost going to get the analytical solution, but because we're dealing with hyperbolic signs, I had to use Wolfram Alpha to produce a particular solution. So what we do to get to this point, we define some convenient constants. So, first we have to, unfortunately, simplify the case of the endpoints in order to get this thing. So we set the curve between the points 0a and ba. So this gives us the minimal surface area between two points of equal height. And this is just so I can show you an actual solution of the equation. So if we plug this into the equation, we get a equals, gosh, C1, and a equals, gosh, right. So cosh C1 equals cosh B1 C0 plus C1. If we just take the inverse of both of these, both sides of the equation, we get a trivial solution where b equals 0. So I'm going to use the symmetrical properties of the cosh curve to say that cosh C1 is also equal to cosh negative C1. And now we can take the inverse cosh both sides. To C0. So we have a relationship between the constants, but unfortunately it's going to get worse before it gets better when finding the actual constants of a particular solution. So we're never going to get a explicit function of the endpoints and x to produce the function of y. We need to go through some intermediate solutions of values and also examine roots of the curves, which is cosh x equals x. So it becomes this complicated thing where you have to find the roots of the intersection between two sides of an implicitly defined function. But because I prepared earlier, I can show you how it works. So what we set is this function, this constant sigma, which, because it only involves capital A and B, it's a property of the endpoints. So it's a measure of how tall it is with respect to how wide it is. And that really defines what kind of solutions we can get. And we also get this constant gamma, which is G1 C0, it's negative C1, but like that, which is going to cause us some strife. But the way we do it is we do some rearranging of our equation up here, and skip the bottom part. What we get is and like I said, it's going to get worse before it gets better with this one, but we can use the point y of b equals a to find our equations for sigma and gamma, such that we can find solutions for gamma. So at this point, the only thing we're trying to find out is gamma itself. So plugging in this point, alright, that is the equation of the roots we will find for gamma. So there is because the whiteboard, because we're looking at the intersection between sigma x and cosh x, there's going to be a certain point at which they will intersect. So there's a certain value of sigma, which is the slope of this line, where there'll be one solution because it touches the curve here, there'll be another one where there's two solutions after this critical point. So that value turns out to be the critical point of sigma c is not particularly interesting. It's something like 1.508880. But if you have, the interesting thing about that is that it tells us that our ratio 2a on b must be greater than 1.5080. So we can't find solutions for the catenary curve if the amplitude, the height of the curve isn't big enough with respect to the cross. So, new page. Using a specific example, we'll go with the curve between the points 0, 5 and 2, 5. Now, this gives us sigma equals 2 equals 5, which gives us our curve 5 gamma equals cosh gamma. So, using Wolfram alpha, well acknowledged that it is, we find that this presents two solutions because the sigma is 5, which is greater than this critical value. And so we get 2 roots of gamma, which is 0.204184 and 3.57607. So these gives us two curves, which could maximize, minimize, or the other critical points of this minimal surface area function, which are there's a practical example of between the curve between 2 points 0, 5 and 2, 5, we get our two Koch equations that are possible minimal surface area solutions. So 0 and 2. Yeah, these two curves. So one of them is really small, and one of them dips a lot. Whether or not these are minimal surface area is not for me to tell, that's for later chapters. But, yeah, there's a solution that can be presented using the Euler-Lagrange equation and deriving the quantum conditions to minimize surface area. Thank you.